Hello everyone, this is Unofficial Sando. Today let's look at the problems Leetcode 465 optimal account balancing. If you like my videos, please subscribe my channel, and you can find the complete prepared list in video description below. Let's move on the problem. So in these problems, we are given a list of transactions. Then we need to set up all the depths in the minimum transactions. Let's directly jump to the examples so to understand problems. So first example is very straightforward. People 0 need to give people 1 $10, and people 2 need to give people 0 $5. So there's not any optimization we can do. So we directly using the two transactions to settle the debt as given by the input. The more complex part is in example 2. Here, I basically make a direct graph to describe problems. Person 0 need to give person 1 $10, and 1 need to give 0 $1, and person 1 given person 2 $5, person 2 to given person 0 $5. So I think one really straightforward idea pop out to kind of simplify this graph is we have a table for each person, right? So then we can fill the table based on each transaction first. For example, we start with the first. So person 0 give out person 1 $10. So we are making the positive numbers as the dollars the person need to give out. So if you look at the graph, so person 0 will give out $10, receive $1, and receive another $5. So eventually he will receive he need to give out $4. And person 1 he will receive $10 given 1 and given another 5. Eventually he will receive $4. And person 2 receive 5 and give out 5. It ends up $0. So based on this table, we can easily find we only need person 0 given $4 to person 1, then we setting up the total debts. So the minimum transaction will be 1. So let's look at how we utilize this naive ideas to come up to the final solution. As we talking before, so at first we can generate this table by giving the examples here, and we can generate the total tables, right? Just iterate all the transaction. Let's see how we end up in the final one. So at first step, our person 1 need to give person 0 need to give person 1 $10, and person 0 positive 10, person 1 minus 10. Then come to the next. Person 0 person 1 need to give person 0 $1. So person 0, since he's received $1, it becomes 9, and person 1 give out becomes minus 9. Then after we finish all the transactions, we will end up person 0 need to give out $4, and the person 1 need to give minus 4, and the person 2 0. For this example is pretty straightforward to figure out. However, for some complex input, we can come up very difficult tables, which we need a step 2. In step 2 here, we do the depth search for this balance list. So here is examples. Person 0 need to give out 3, person 1 need to give out 7, person 2 need to give out 5, person 3 need to receive 7, person 4 need to receive $8. So the way we do the depth search is we start from the first index, then we are looking for the later index which value is the negative side of the current values. So here we have -7 and -I, and we're trying to make current peoples as 0 total amount. So basically it's change the total status of the balance sheet. For these ones, if we change to 0, which means we giving the $3 to this one, so this guy will become -4. Or we can try for this guys become -5. Then after this guy becomes 0, we can move to the next one and the next one, and until the whole sheet all becomes 0. We can calculate the total transaction. Let's look at how we formulate the whole search trees by trying all the ways to finish transactions. So when we first start, of course our transaction right now is 0. Now we trying to make first people as 0. So here is we given the -7 $3, so it becomes -4, and or we can try given the last guys $3 become -5. Here we all take transaction 1. Let's go next. Given the time and the space limitation, I just skip this part, but we are reach the end of those branch of the solution. So we come to the next, right? So we try to make this 7 as 0, so we can either give -7 or give it -5. So here we give this -7, so -7 become 0. Here if we given $7 to the last guy, it becomes 2. So at these steps we are spend 2 transactions. And for this direction we only have 2 non-zero values, so we just give this 5 to the last one. Eventually we will settle the debt. So for this one, we start from 5 here. So there's only one have negative size here, so we only need to give 5 to -7, so it becomes -2. Then we do another transactions, we settle the debt. So when we search all the solutions, for depth first search, there's usually an optimized way to pruning the branch. So based on the one key observation, we can pruning this branch, which is that we can observe that if we give 7 to -7 here, both 2 people become 0, right? So this is definitely the optimal solutions. We setting the 2 people depth to 0 in only one transaction. So this is why we want to go into this direction, but we want to pruning this direction. So it turns out the minimum transaction is also in this direction, but not in the directions we are already pruned. And next, let's look at the code. So when we start, we have implement the first step, which is to generate the balance list. So here we have a hash map here for each peoples we calculate what's the total debt he need to either to give out or receive. Then we formulate the balance list by using the hash map. Since here we declared new variables, data container here, so space complexity can be equal of n. Here we complete all the balance list. Since we need to iterate all the array, so computation complexity becomes bigger of n. After we complete the first step, we will start the second step, which is depth first search. So so the kind of different what I described in the slides before, which is from the top to bottom. So here, depth first search implement is more based on the bottom to top way, which is the backtracking. So in here's when the index go to n, we just end the whole depth first search, which is the end condition of the backtracking or the recursion condition. Then if the balance list value equal to 0, of course we don't want to use this to balance other people's value, since this guy is always 0, so we directly jump to the next one. So next we come to for loop iterations. We figure out all the later value which has negative sign of the current value. Then here we update our minimum transactions based on compare with the current local minimum and compare with the minimum transaction of the later plot, which is the bottom to top way to do the backtracking. Here we +1 because here's we cost off one additional transactions. Then next if we find the current the way to balance the sheet is equal to 0, that means we can pull in later solution, right, as I mentioned in previous videos. So we directly break here because we already find the minimum transactions for this status. Here also please pay attention. So previously we changed our status by using current balance solutions. Then here we need to recover it back. So this enables us to find the other solutions. So this is the basic templates for depth first search backtracking version. So eventually we finish all the iterate all the values in the sheet. We directly return the minimum transaction. How we estimate the computation complexity for depth first search? I think one way is you can consider like as this. So to make all the status, think about an array, it's a binary array, either 1 or 0. We need to make some numbers from 1 to 0 or 0 to 1. So this comes out to 2 power of n total status, right? This is the search space of the problems. And for each solutions, we also need to do the big of n to complete this solution, to complete these 4 loops in worst case, right? For each status, and we have big of n for loop iteration. So eventually, the worst case of the depth first search complexity will be 2 power of n and then multiply n. Then the total computation complexity is we take the maximum big of n and the big of 2 power n multiply n. So that will be big of 2 multiply n multiply n. Yep. Okay. So that's the what I want to talk about today. And please left your comments and suggestions as below videos. And see you next time.